Hi, everybody. You don't see my picture now, but I'm welcoming you to, actually, I'm gonna show you my picture in a second so you can see how handsome I am. This is me. Hi. I'm gonna shut the video off now, so you'll just hear my voice and see the screen. Anyway, the least common multiple of two or more integers, section 1.10. I'm going to go through some stuff here in the textbook, and then I'm going to show you some stuff on my scroll. Anyway, the least common multiple of two or more integers. So the common multiples of two or more numbers are the multiples of their least common multiple. That's really interesting. So let's see what that means. First of all, just what does that even mean? And I'm going to show you this right here. So here's two numbers here. Let's say 8. And the multiples of 8 are 8, 16, 24, what's next? 24, 32, 40, 48, oops, 56, 64, 72, 80. And of course, this goes on forever. And the multiples, let's say 6. Let's put 6 over here, actually. The multiples of 6, for example, are 12, 18, 24, 30, 36, 42, 48, 54. What's next? 60, 66, 72, 78. That's right. Yeah. All right. So if you notice, there are certain, these are the multiples of 6, 6, 12, 18, 24, so forth. And these are the multiples of 8, 8, 16. There are certain numbers that are on both lists. For example, the number 24. 24 is on the top list, and it's also on the bottom list. It's on both lists. And what else? 48 is on both lists. And I think I noticed another one, 72 is on both lists. And there we go. And you may have noticed, if you're very sharp, you may have noticed that the common multiples, so a common multiple means it's on both lists. Well, notice that 24, 48, 72, notice that 48 and 72 are multiples of 24. So that's what all this is. That's what this means here. The common multiples of two numbers are multiples of their least common multiple. And we're going to prove this now post haste. So we're going to give a proof as follows. Consider the fact that in the case of two numbers, let's call them M and N. So M is my first number and N is my second number. Mike, November, MN. And let's say that these two numbers have a greatest common divisor, which is a different concept. And we're going to call that D. So M is D times some other, some leftover. N is D times. So in our example that we gave over here, D, in the example that over here, D would equal, oops. D would equal 2. So 6 equals 2 times 3, and 8 equals 2 times 4. And that's what we're saying here. So M is equal to d times mu, and n is equal to d times v. Notice that mu and v are going to be relatively prime because any common factor is absorbed into d, and mu and v have no common factors left. So the common multiples of m and n are comprised of numbers. The common multiples of m, I'm sorry, are numbers of the form a times m. But m is equal to d mu, so it's a d mu. And a is any integer, whatever, as long as it's an integer. Now, in order that these numbers shall be multiples of n, it's necessary and sufficient that a d mu shall also be a multiple of dv. So a mu has to be a multiple of v, and a, which means a has to be a multiple of v. Now, mu and v are relatively prime. So writing that a equals delta v, we have as multiples in question the set delta d mu v, where delta is an arbitrary integer. And that's my multiples. This proves the theorem in the case of two numbers that d mu v is the least common multiple of m and n, and delta times d mu v is any multiple of that least common multiple. Now, now we want to now I want to show you some general information about LCMs and Gcfs. And this is really how I teach. I teach this to like a whatever, pre-algebra class. So here I have two numbers, 12 and 18. So 12, if I write the prime factorization, 12 is 2 to the second times 3. 18 is 2 times 3 to the second. Well, if you want to find the GCF of two numbers, this is really how I teach classes. You take the product of the smalls, meaning that you have 2 to the second power, and here you have 2 to the first power. Well, 2 to the first power is smaller than 2 to the second power. I usually don't bother writing, first power, but I'm doing it here just to be clear. And I guess here I'll write also first power. And 3 to the first power is smaller than 3 to the second power. So I take the smalls, which is 2 and 3, multiply them, and I get 6, and that is my GCF. Meaning 6 goes into 12, and 6 goes into 18, and 6 is the largest number that goes into both 12 and 18. And to find the LCM, I take the product of the bigs, meaning that 2 to the second is bigger than 2 to the first, and 3 to the second is bigger than 3 to the first. So I take the bigs, 2 to the second, 3 to the second, multiply them, and I get 36, which is the LCM. Because 12 goes into 36, and 18 goes into 36, and 36 is the smallest such number. And as we saw from the theorem that we just started this class with, any common multiple of 12 and 18 will be a multiple of 36. Let's take two other numbers, 30 and 100. Now 30, the prime factorization is 2 times 3 times 5. I usually don't bother writing first power because it's obvious, but I just want to contrast and compare things here. And let's look at the number 100. Well, 100 is 2 to this, well, it's 4 times 25. So it's 2 to the second times 5 to the second. Now, I usually wouldn't bother writing 3 to the 0 power. It's usually don't bother writing that, but I'm writing it here just to make a point. So you see where this is all coming from. And I guess just to be consistent with that, let me just to be consistent with that, let me and I guess I'm gonna put a little multiplication next. I like those. And let me just bold that. I want my okay, so 2 to the first times 3 to the 0 times 5 to the 1. Well, these are the smalls, and that's 10. And 2 to the third times 3 to the first times times 5 to the second is, these are the bigs, and that's really 4 times 3 times 25, which is 300. So 30 and 10, the GCF is 10, the LCM is 300, because 30 and 100 both go into 300, and that's the smallest such number. 10 goes into 30, and 10 goes into 100, and it's the largest such common number. Now, it turns out, based on this argument, that the product of the GCF and the LCM is going to equal the product of the two original numbers, because either way, you're multiplying all the bigs and all the smalls exactly once. So that's kind of cool. So notice, in other words, 6 times 36 is, let me just write explicitly here. 6 times 36 equals 216. And 12 times 18 equals 216. So the GCF times the LCM is equal to the product of the two numbers. And I'll write the same thing over here. 10 times 300 well, that equals 3,000, even I knew that one. And then 30 times 100, that equals also 3,000. So you see that, and it makes sense because the GCF and the LCM, the GCF is all the smalls, the LCM is all the bigs. When you're looking at these two numbers and all the prime factors, each factor is either big or small, and it's like lick the platter clean, because you have all the, what's the thing? Jack Sprat ate no fat, his wife could eat no lean. So between the both of them, they lick the platter, because everything's either fat or lean. Everything is either big or it's small, and that, my friends, is the story. Well, that's all I wanted to say for section 1.10, and that is the end of this recording. It's been loads of fun.